Hello and welcome to the Chemistry Academy. In this video we're going to go over an introduction into pH in relation to the Advanced Higher Chemistry course. So back in National 5 we learned that water is partially ionic and the water molecule H2O actually breaks up to form H plus and OH minus ions, hydrogen and hydroxide ions. However, at Advanced Higher we learned that hydrogen ions in solution, so H plus AQ, is not actually a thing that exists because the hydrogen ion is not stable enough to float around on its own. So what actually happens is it joins onto a water molecule and forms this thing here, H3O positive, which is known as a hydronium ion. So when it comes to pH in Advanced Higher, you want to think of hydronium as hydrogen ions. And if you are thinking of writing hydrogen ion in terms of pH and things, you should really be writing it as hydronium H3O positive, because like I've just said, H plus in an aqueous solution is not stable enough to exist. So what happens is the hydrogen ion attaches itself to a water molecule to form the H3O positive. But the same fundamental theory still is correct. It does. A one water molecule will dissociate in order to form a hydronium, which is essentially the H plus, and OH minus, the hydroxide ion. So we essentially have two water molecules combining here. One of them dissociates, i.e. splits up, gives a hydrogen to one of the water molecules to form this, and then the hydroxide ion stays on its own. This means that water is classed as being amphoteric, so that means it can act as an acid and also a base. Remember, a base is something that accepts a proton, so accepts an H plus, which is what's happened in this instance. The water has accepted a hydrogen ion, so that means in this case it's behaved as a base. An acid is something that donates a hydrogen ion, so in this case we say this water molecule has donated a hydrogen ion and ended up becoming hydroxide ion. So in this case the water has acted as an acid because it has donated the hydrogen ion. Okay. We can then talk about conjugate acids and conjugate bases. So these are a little bit confusing, but essentially the conjugate acid is the acid that forms once the base reacts. So once the base has accepted the proton, then that product is now an acid because it's got an extra proton that it can then go and donate. So if we say that this water molecule here is the one that accepted the hydrogen ion and therefore is the base, then the base becomes the conjugate acid. So the hydronium ion would be the conjugate acid. If we say then this water molecule was the acid, the one that donated a hydrogen ion or proton, then this becomes the conjugate base. So the base becomes the conjugate acid and the acid becomes the conjugate base. The conjugate base is now a base because it is able to accept a proton, an H plus, because it's got that negative charge. So that's how the conjugate acids and bases work. They're the acids and bases that are formed as a result of the opposite thing reacting in the first place. Okay, so the bases form conjugate acids and the acids form conjugate bases. But we'll go into that in more detail in my acids and bases tutorial for Advanced Higher, but just to show you that it does kind of tie in here and shows you how water can act as an acid and also a base. So just remember this word here, amphoteric. Because water does dissociate and split up into these hydronium ions and hydroxide ions, we have this equilibrium, so we can write an equilibrium expression, which is the equilibrium expression for the ionic product of water, or the dissociation of water. Kw is the constant that's known as the ionic product of water, so that's essentially the equilibrium constant for the dissociation of water molecules. You'll notice, if you've seen my equilibrium constant video, you'll know that it's always products over reactants, which means that it would have to be the concentration of these products over these reactants. However, pure liquids and solids are not included in equilibrium expressions, so the H2 molecules are not included, which is why we've just got the hydronium concentration times the hydroxide concentration. Anything that's ever in square brackets in equations just means it's a concentration that we're talking about. Okay, so this is the expression for the dissociation of water. And what you need to remember is that dissociation constants, and also therefore the ionic product of water, are dependent on temperature. So if you change the temperature, you will change what this ionic product of water value is, which means that you will then have more of these ions in solution or less, depending what the temperature is. So changing the temperature can change where the equilibrium sits and what this equilibrium constant is. At roughly 24-25 degrees, the constant, the ionic product of water value is 1 times 10 to the minus 14, but that will increase with increasing temperature. So the value of the ionic product of water will increase with increasing temperature, and this is because the dissociation of water is an endothermic process. So if you remember, when it comes to equilibrium, it's good to remember intendo. So increasing temperature favours an endothermic reaction. It's because the forward reaction here, the dissociation of water, is endothermic. With an increasing temperature, it's going to favour that forward reaction. Therefore, you're going to have more of these ions in solution. Okay, if you've got more of the ions, you're going to have more hydronium ions, which is essentially the hydrogen ions. Therefore, your pH is going to be lower, because remember, pH stands for power of hydrogen, and the lower the pH is, the higher the hydrogen ion concentration is. So if you're increasing the temperature, you're going to increase the dissociation constant, or the ionic product of water, and therefore you're going to have a greater concentration of the hydronium ions, which therefore means your pH is going to be lower. So there was actually an open-ended question in one of the past papers, I can't remember which year it was, that was about a student using a pH meter, and they measured the pH of the solutions at different water at different temperatures, and they thought their pH meter was faulty because it wasn't pH 7 every time. But with increasing temperature, the pH will drop slightly, not massively, but it will drop slightly, and that's because of what I've just explained here. The dissociation of water into its ionic form is an endothermic reaction, so with an increasing temperature that's going to be favoured, and you will get an increased concentration of hydronium and hydroxide ions, which will therefore give you a lower pH. Okay, so that's kind of the main theory around the dissociation of water, and then the equilibrium associated with it. So what we're going to look at now is some of the important calculations or equations that are often involved with pH. So you will get these in your data booklet. The main ones, now these ones are for things that are only that fully dissociate, so completely split up. So dissociation means splitting. Weak acids and weak bases don't fully dissociate. They'll only give away or accept some hydrogen ions. I will do a separate video on weak acids and bases, but just bear in mind that these equations here are just for solutions where there's full dissociation. So that would usually be like hydrochloric acid, sulfuric acid, sodium hydroxide, any of your common lab acids and alkalis. Okay, when the pH of water or solution is 7, the concentrations of the hydronium ions and the hydroxide ions will both be 1 times 10 to the minus 7. This is just something that you probably want to try and remember, but it's quite easy to remember because when the pH of 7 is 7, the powers will be, of these two things, will be to the negative 7. Okay, if you look down here, this shows you how that is the case. So the concentration of hydrogen ions, which that should technically be H3O positive, that is equal to 10 to the power of whatever the negative of the pH is. So here the hydroxide ion concentration is this, which means the pH is then 7, because whatever that negative power number is what the pH will be. That's only the case really if you've got a 1 here, like reading it off. If there was another number, you would have to use this equation here to work out. So you'd have to put the hydrogen ion concentration in there and just plug this answer in, the numbers in. But we're going to do a question like that in a minute anyway. The other thing that is important to remember is the pH and pOH relationship. So these are the equations you would use when you're trying to work out the pH or the pOH for a solution that fully dissociates. And it's just negative log to the base 10 of whatever those ion concentrations are. Okay. pOH is the power of hydroxide ions, so that's related to the concentration of hydroxide ions. pH is the power of hydrogen, so that's related to the hydrogen ion concentration. The relationship between pH and pOH is that they have to add up to 14. So if you know the pOH and you want to work out the pH, you would just do 14 and take away the pOH. If you know the pH and want to work out the pOH, you just do 14, take away the pH. So in either case, you do 14, take away the one that you know. Okay, so they always have to add up to 14. So let's go through some of these questions just to put these sort of relationships into practice. And these are some things that can come up in your exams. So the first question is working out the pH of a 0.01 mole per litre hydrochloric acid solution. Now, because there's a 1 in this concentration, because it's like 0.01 or even if it was 0.1, then what we can do is change this concentration into scientific notation, and the power on the scientific notation will be our pH, or the negative pH. So if we do some scientific notation, this would be 1 times 10 to the power of minus 2, which means our pH is 2, because the number on the negative power is 2. Okay, now like I said, that only works if this number is 1. If this number is anything else, we have to plug it into the pH concentration with hydrogen ion concentration in it. So this is what question 2 is showing us. So let me just grab my calculator. So we're working out pH of the solution with a hydrogen ion concentration of 0.26 moles per litre. So we use the equation, my pen's not very good, sorry. So the equation we use is pH equals minus log to the base 10 of the hydrogen ion concentration. So when we plug in the number, we get minus log to the base 10 times by 0.26. And putting that into your calculator, it's been a very long time since I've used a log button. So we get 0.585, or we'll just say 59. Okay, so that would be the pH of that solution. Then when the question 3, working out the hydrogen ion concentration when the pH is 9.2. Just change this one because in the data booklet it's written as H3O positive. This one here is in the data booklet, well, it's not given to you in the data booklet, so you can remember this, try and remember this one if you want, or you can, if you're good at rearranging equations, can rearrange this one. So I'll show you how to rearrange it, because just in case you don't manage to memorise this one, but plugging it in is pretty straightforward. If the H3O plus concentration is working out that when it's pH 9.2, you would just put in your calculator 10 to the power of minus 9.2 and then press equals, and it will give you out the result. But if we plug it into the pH with the hydronium ion concentrations, we've got pH is 9.2 equals minus log to the base 10 of H3O positive, which is what we should work out. So we need to take the negative across first, so that becomes minus 9.2 equals log base 10 of H3O positive. And then the inverse of a log is 10 to the power. So it would become 10 to the power of minus 9.2 equals H3O positive. So as you can see, we've ended up with that, but it's just back to front. So if I plug that in my calculator, 10 to the power of minus 9.2, we get a very small number, which is 6.31 times 10 to the minus 10. Okay, and that would be moles per litre. So very small hydrogen ion concentration. And then, or hydronium ion concentration, sorry. And then question 4 is working out the pH when the hydroxide ion concentration is this. So this is one of the more complicated ones because we're trying to work out pH, but we've been given OH minus, so we need to use this equation to start with because we know the hydroxide ion concentration. And then once we've got the pOH, we can use our pH plus pOH relationship to work out what the pH is. Okay, so just watch out for that. If you're given hydroxide ions, you're going to have to work out pOH first. So pOH is minus log to the base 10 times the hydroxide ion concentration. So that would be minus log to the base 10 times 1.6 times 10 to the minus 4. So plug that into my calculator first. Negative log times 1.6 times 10 to the minus 4. So that gives me 3.79588. So I'll just round it to 3.8. So that's the pOH. That means then that the pH is going to be 14 minus the pOH, which would be 14 minus 3.8, which is, I should really be able to do that in my head, 10.2. So that's the pH. Okay. So that's some examples of different relationships with pH, but most of the time you will use this one, and this relationship here. So all the other things here are really just things that are good to keep in mind when it comes to the ionic product of water and dissociation of water, just in case it does come up in like an open-ended question or anything like that pH meter one that I was talking about. You could potentially be asking multiple choice questions around the theory around it as well. But I hope that helps. I would recommend going and trying some past paper questions on pH calculations just to have a go. Just remember though, some of them are for weak acids and bases, which use a different equation to any of the ones we've done here. So you can check out my tutorial video for them if you need to. If you did find this video useful, please give it a like. Don't forget to subscribe. And also, if you are looking for extra chemistry revision, don't forget I do have my Advanced Higher Chemistry Google Classroom with lots of revision materials in there, lots of quizzes. So there's information in the description below if you want to join that. But failing that, I will see you again soon.